right, we're live. Okay, so this is the first part of the inverse lesson for 1.4. And we're only going to do the first couple pages. First of all, do you remember from grade 10 the difference between a relation and a function? In mathematics, a relation is any connection between x and y, two variables. One single x value may have multiple y values. A function, however, is where an x value has to have a unique y value. So a particular relation where each element in the domain has one and only one unique element in the range. And that's why we called what we did in grade 10 the vertical line test. If a vertical line draws through a graph and only possibly touches the graph at one spot, then that is a function. If a vertical line touches the graph in more than one spot, it's only a relation, it's not a function. Notice a function is always a relation, but a relation is not always a function. So let me draw a couple of examples. First, a relation that is not a function might be something like a sideways parabola, like say this guy here. Right? That's a relation, but it's not a function, because notice it fails the vertical line test basically everywhere to the right of its vertex. But if something's a relation and a function, that means it would pass the vertical line test. And again, it can be a piecewise function where it has a part that's linear and then a part that's, I shouldn't say linear for that. Let me draw that better. A part that's linear, and then, or sorry, I said the word linear again. A part that's constant, and then this is what I meant. A part that's linear, and then, oh, after that it could even curve if you wanted it to. There we go. That would be a piecewise function made up of a constant and a linear and a part of a quadratic. But it's still a function, because everywhere I draw a vertical line through it, I'm only going to hit it once. The inverse of a relation is found when the x and y values are interchanged. So the mapping notation is that xy becomes yx. So for example, the inverse of the relation -1 becomes 4 and 3 becomes 5 and 6 becomes -2 would be the set 4 becomes -1, 5 becomes 3, and -2 becomes 6. Now, are the two relations above functions? Well, let's see. Do any x values repeat? No, I don't see any. Let's look at the inverse. -4, 5, -2. No. Yes. No x values repeat. Remember, for it to not be a function, an x value would have to repeat, and then it would have to have a different y value. You don't have to write this down, but let me just show you what I mean by that. For example, this set of points here would not be a function. If I had 1, 2, 2, 3, 3, 4, those are all fine, but then all of a sudden I have 2, 5. See why that wouldn't be a function? Right? What kind of mathematical formula would you plug in the number 2 and then out comes a 3? Oh, but then the next time I plug in the number 2, out comes a 5. Functions don't work that way. Functions always give you the same thing. I always tell my grade 10s, I think of a function like it's a toaster. You put in bread. That's my toaster. You put in a piece of bread, push down the little thing, and out comes toast. Every time you put in bread, you get toast. Could you imagine if you had a machine that you put in bread and then out comes a Pop-Tart? You put in bread, out comes a bagel. You put in bread, out comes a whole sandwich. Who knows what comes out? That would be a relation. It would not be a function. Every time I put in the number 2, I should get the same number out again if it's a function. So that's not a function. All right, moving along. Given the relation below, sketch its inverse. So what's the inverse of this thing? Well, I think I'm going to have to actually make some points so that I don't mix this up. So, and I'm going to do this in a different color so that it's different than the black lines on the page. So the points x, y on my original are going to become, actually, why don't, here, let's do this. Let's do these in black. The original points that are x, y are going to turn into the points y comma x. So on my original graph, that first point on the left there is negative 2, 1. So it's going to turn into 1, negative 2. So this point here is going to turn into 1 over and 2 down. There it is there. Now, I always go in a direction so that I always connect points properly. You have to connect the points that you're mapping in the same order as the things they were being mapped from. So the next point, the point that the first one here is connected to, is the point, what is that, negative 1, 2. So what's that going to map to? It's going to map to its inverse, 2, negative 1. So it's going to move over 2, negative 1, and these things are, of course, connected with a line. So I just did this line here. All right, the next line in the row is 1, 2, and that's going to map to 2, 1. Okay, where's 2, 1? 2 over, 1 up. So this line here is right. Oh, hang on a sec. I just wiped out my point. 2, 1. 2, 2, 1. There we go. That line that I just highlighted a second ago is right here. There we go. And lastly, the point that starts off, I'm on top of it now, but it's the point 2, 0 is going to map to 0, oops, that didn't work. Is going to map to, there we go, 0, 2. So 0 over and 2 up is right there, and then join those 2 points. There we go. Note, the original graph is a function, right? The vertical line would never cross that black line more than once. The graph of the inverse is not a function. It is possible to determine whether or not the inverse of a relation is a function without having to physically graph it. This can be done by using the horizontal line test on the original function. Note, the graph of a relation and its inverse have symmetry over the line y equals x. In other words, you can say that that original black graph and the purple graph are reflections of one another if the reflecting line is the diagonal line y equals x. This takes a little bit of imagination. Can you kind of see that? If I turn that dotted red line, which is the line y equals x, if I turn that into a mirror, that's an X up there, by the way. That's better. Can you kind of see that that's a mirror image? Right? This point here reflects over there. This point here reflects over there. See how it works? Of course, this point is not going to change because it's on the reflective surface. Ooh, what do we call it again? Begins with an I. That's an invariant point. There we go. Now, state the domain and range of these things. Okay, so my original function, the black one, let's go back and look at it. The black one goes from x is negative 2 all the way to x is positive 2. So that one's going to have an original domain from negative 2 to 2. If you don't like interval notation, of course, you can write it in set notation. What's the range of the black one? Let's see. What are the y values? Well, the lowest y value we get is down here at 0. The highest value is up here at 2. So in interval notation, we go from 0 to 2. And in set notation, that means y is greater than or equal to 0, less than or equal to 2. But what about my new one? Let's take a look. So for my purple one, for the domain, well, the domain, I start at 0, furthest left, and I go the furthest right is 2. So 0 to 2. And again, if you'd prefer set notation, write it like that. All right, let's look at the range. What are all the things y can be on the purple one? Well, the lowest y thing is -2 down here. The highest thing is +2 up there. So I'm going from -2 to 2. What do you notice? Yeah, there it is. Let's put that. Domain and range switch when you take a relation's inverse. Okay. All right. When an inverse is a function, so if we take the inverse of something and it happens to be a function, we use this notation. Oh, I feel sorry for these little symbols because we use them for so many things. It's like, couldn't you have invented some new symbols for inverse? Well, hundreds of years ago, they started using this symbol, and they're not going to change this because we don't like it. If the original function is f of x, the inverse is f to the -1 of x. That is not the same thing. Oops, hang on. Sorry about that. That's not the same thing as reciprocal. I know it's confusing because you've learned that, hey, if I take a number to the power of -1, that's just a reciprocal. But this thing here is not an exponent. You've seen this before, where what looks like the exponent of -1 isn't really an exponent. It's just, what's the word for it? It's just a superscript. Do you know what I mean by superscript? Right? In chemistry, when you have, C6H12O6, those 6's are not exponents, right? They're subscripts, right? And when you're doing valences, you might have something like, +1, right? That's a, or 1 plus. I actually wrote that backwards. That's a superscript, right? It's not an exponent. So you've seen symbols like that in chemistry, but specifically, think back in math. You've seen -1 like this, not used as an exponent, back in trig. Remember trig? Say you had something like the sine of theta is equal to 1/2, and you want to know how much theta is. Do you remember what symbol you use? Is this the reciprocal of sine? No, it's not. It's the inverse of sine. So remember that? Inverse of sine. You are not taking a sine and putting it as 1 over sine. You are not reciprocaling it. You are not doing the same thing here that you'd be doing there. That's not what the symbol means. So this is an important note. That is not taking the reciprocal of a function. All right, moving on. If the graph of f of x contains the point 3, -4, determine a point. I think they meant to say that. Come on, pen. There we go. That must be on the graph of the inverse. So, if 3, -4 is on the original graph, -4, 3 must be on the new graph. All right. Example 3. Determine the equation that represents y equals f to the -1 of x. Okay, well, let's see. How are we going to figure this out? Well, remember that f of x is the same thing logically as saying y. The y values are the f of x values. So now, the next step I'm going to use is switch x and y. So to do the inverse, I would say that if y equals 3x minus 1, x must equal 3y minus 1. There, I just did the inverse of that equation. Now what? Now, rearrange the equation so it is in terms of y. So, okay, so right now it's x equals 3y minus 1, so I'm going to add 1 to both sides. Would it make more sense to you if I just said isolate for y? Okay, so how do I get this y by itself? What's the next step? I'm going to divide both sides of the equation by 3. And then that's it. Remember that y can be said to be f of x. But f of x was already defined as 3x minus 1. This thing isn't f of x. It's the inverse of f of x. And that's how we do those. Okay, that's as far as I'm going to go for today. We'll finish up 1.4 tomorrow while you guys are watching on Teams. And if there's anybody here done 1.3, you feel you're kind of done with it, you actually could start the 1.4 assignment. You just can't do it all yet. Let me take a look. We're going to do those examples tomorrow, and we are going to do that lesson tomorrow as well. So let's see. You could definitely do 1.4 number 1 if you wanted. And you could do number 2. And you could even do number 3. And I'm actually going to say let's not bother with number 4. Number 4 is kind of a dumb question. So actually, so you know what? Actually, you pretty much could do most of it. Well, wait a minute. Can you do all of 3? Let me take a look at 3. Yeah, don't do 3H. That's what we're going to talk about tomorrow. So you could get started on 1.4 if you wanted. If you want to wait till we finish the lesson tomorrow to start it, you can. Maybe just try the pictures. Just try 1 and 2 for now. Okay, yep. Oh, of course. Okay, so I'll amend the, I'll update the blog, because I did say that there's no new assignment, and I guess technically there isn't, but if people, I'm getting the sense that there's some people who are done 1.3 and don't need any more time on it. Again, if you want more practice on 1.3, you can just do the textbook questions. But let's see. Let me go to log. There we go. If you are ready to move on, you can start the 1.4 assignment on page, what page of the booklet does the 1.4 assignment start on? 20 something? I think my booklet's different than yours. Oh, it's in the 30s. Is it 32? 32, thank you. Oops. So there we go. Oh, I guess I could stop the video too. So there we go. That's what I'll say on the blog. And the video, we'll continue the video for 1.4 tomorrow.